All right, so let's try and actually find the velocity functions and acceleration functions for the position function with respect to time. That is 4t cubed minus 8t squared plus 3. Go ahead and solve those. All right, so for our velocity function, the velocity function, which is really going to be the derivative of the position with respect to time, we're going to apply the power rule here, and we get 12t squared minus 16t, and this is a constant, so that goes away. And the acceleration function is the derivative of the velocity function with respect to time, which is going to be 24t minus 16. So this is the acceleration function with respect to time, velocity with respect to time. And the question I have for you, is this considered uniform accelerated motion? Well, hopefully you saw that it's not UAM. This is not uniformly accelerated motion because the acceleration rate is changing as a function of time. So this we could not apply the UAM equations to. All right, so let's take a look though. I'm just gonna mark this off here. And let's look at a UAM situation. All right, so let's say that we're going to take this baseball and we're going to throw it straight up into the air. And the initial position, I'll use y sub naught. That ball is getting released, let's say 2 meters above the ground. And the initial velocity in the vertical is going to be, let's say, 26 meters per second. And we are throwing it straight up into the air, so we're going to deal with the acceleration, which we know is negative 9.8 in the vertical meters per second squared. So we could say this is the y acceleration in the vertical. Now, we know we have 3 variables out of the 5. We could use our UAM equations, but I want you to look at how we could leverage and use derivatives to help try and analyze this motion problem. Okay, so what I want to first do is, let's create the position function, right? Vertical position with respect to time based on the information that we have. 2, let's do velocity. Again, in the vertical direction here, so this is v sub t. Let's find the acceleration function. You may have an inkling and understanding of what this actually is already, but let's just go through the process. And then 4, what I'd like to do is actually determine the time to get to the max height. And then 5, let's say, well, what is the max height? Okay. And how can we use derivatives to help us analyze this? Well, let's break this information down into our functions. So let's start with number 1 here with the vertical position function. So y sub t is going to be, well, we know our position function in UAM equations, that is we have constant acceleration, so this is going to be my initial vertical height plus my initial vertical in the y times time plus 1/2 AYT squared. Just getting that on there, okay? So let's go ahead and plug this in. So y sub position function, well, this was 2 meters plus my initial velocity was 26 meters per second times time plus 1/2 negative 9.8 meters per second squared. And this really should be running out of space here, t squared. Okay, so that will give us 1/2 at squared. It's our position function there. So let's look at 2 with the velocity. So if I take the derivative of this, my velocity function is going to be dy dt. Well, this is a constant. This blows away. I have first order power of time here, so this becomes 26 meters per second plus, well, the t squared, I bring the 2 down, I have 1/2 here, and this really just becomes negative 9.8 meters per second squared times time. Now, this may look familiar to you. I don't know if you recognize this, but what is this? This is really the initial velocity in the vertical direction. This is our acceleration. This is really our first uniform accelerated motion equation, where velocity is equal to initial velocity plus AT. So just wanted to point that out to you as you're working through these derivatives. Well, here's this velocity function based off of the uniformly accelerated motion equation. All right, let's find the acceleration. Well, to take the acceleration of this, well, there's no time component in this term here, so that goes away. This is t to the first. So acceleration with respect to time, which again is dv dt, or the derivative of the velocity function with respect to time, is just negative 9.8 meters per second squared. Wait, so you're saying this is a constant acceleration rate? Yes, this is uniformly accelerated motion. We're in free fall here. All right, so nice. We just worked through 1 through 3. And number 4 is time to max height. Well, to look for time for max height, I want to actually look at this graphically. Let's take a look at this graphically. What does this look like? Okay, so here is our position versus time graph, or vertical position versus time. We also have a velocity versus time function. And let's talk about acceleration here as well versus time. Okay. Well, what is this going to look like? Well, really what we're talking about here is we threw the ball 2 meters above the ground is where it was released. It's going up and then coming back down here. If I were to track this point in time down to my velocity, there's important things that I know about this here. Okay, well, we start off with a positive 26 meters per second. If I were to look straight across here, boop. That's going to be an important point right there too. Oops, looks like I should have carried that out a little bit, but if this is my 26 meters per second, I know that at this point my velocity in the vertical should be 0. That's where my maximum height is. So if this comes across through that point, if I did a better job of carrying this line down, and then it ultimately falls to the ground here. But at this same relative height on the way back down, 2 meters above the ground, it should have the same speed, just in the opposite direction. So again, I'm just applying some of my graphing knowledge here to this graph. But again, the last piece here would be the acceleration is constant, and we are at negative 9.8 meters per second squared. Okay, great. Well, what does that mean? Well, what we're pointing out here is that this velocity function is the first derivative of the position function. And what do we have occurring here? This is what we're calling a localized maximum value. So this right here, where the slope is 0, so that means that dx, or in this case dy dt, is also equal to 0. This is a local maximum. Okay, so whenever you have when your first derivative of your position function is equal to 0. So when, let's say, dx dt is equal to 0, then you have a local maximum value, minimum value, or some type of transition, as is in the case with when you have something to the cube root, right? So if we look at the function y equals x cubed, we're going to get something that looks like this. In which case, at 0, you're going to have a derivative here of 0, but that's going to be a transition. Okay. Turns out that when you have a maximum value, the second derivative of your acceleration, second derivative position, which would be your acceleration. So here's your first derivative. Okay, so right, this is dy dt, and this is the second derivative of the position function. Okay, first derivative, second derivative of the original position function. When this second derivative is negative, you're having a localized maximum with a concave down. Okay, and the reverse would be true. If your second derivative is positive, most likely then that situation is you're going to be having a localized minimum. So if we know that that's what's happening here, we can use the derivative, the first derivative, the velocity where it's equal to 0, to find both the maximum. Well, ultimately we'll find the time first, and then we can solve for the max height using the position function. So getting back over to this then, if I want to actually find what is the time at which I'm reaching this maximum height, it's when this velocity function is going to be equal to 0, because this is velocity with respect to time. So come back over here to my velocity function, and I want to set that equal to 0. So here we are, number 4. We're going to say that the velocity function is equal to 0, which is equal to 26. For space, I'm going to drop the units here, and it's plus and negative, so I could have just left that as negative, but 9.8 times t. I'm solving for t, so I'm going to subtract the 26, divide by the 9.8, gives me t, which, let's take a look at our calculator here. Let's see, there it is, I have it right there. Okay, but we can do it again. So negative 26 divided by, negative 9.8. So it's going to give me a time of 2.65306. Okay, so there's my time in seconds. And then lastly, we're looking for the maximum height. So I'm going to come back up to our position function here, which is laid out right here, and just put in the 2.65306. So if I'm going to plug this back in up here, I'm going to plug in 2.65306 for the time, and then also up here time squared. So after you plug that back into this equation up here, what you're going to find is that your maximum height, so this would be for number 5, y sub t max is going to be 36.4, not 4898, and with 2 sig figs we're going to say 36 meters. That's your maximum height. Again, using the derivative to find a localized maximum based on your understanding of what's going on with the problem can help you do that. So even if you have functions or equations that are not UAM related, using the derivative is still going to help realize that you have a localized maximum where the velocity function is at 0.